Hello. Today we will start with this very well known approximation that went about explaining many of the phenomena in metals for nearly about a century, and this is called the free electron approximation. Although most of the materials are insulating in nature, it is the metals that are of central interest, because many interesting phenomena happen in metals. The earliest ideas about metals before the birth of quantum mechanics was introduced in a very interesting paper by Drude, DRUDE, which constitutes one of the basic postulates of the free electron approximation. Now, what does this approximation tell us? I will tell you the approximations, the set of approximations, and then I will work out one or two problems based on these approximations. Then you will realize how this approximation is used to calculate certain transport phenomena. So, the basic tenet of this approximation is that the electrons that form the conduction electrons in a metal come from the atoms. The valence electrons of the atoms in the solid wander about, leaving their parent atoms, and they wander about throughout the solid, and then they basically form like a behave like a free electron gas. And what one does in free electron theory is to assume that this is like a free electron gas of a density typically of Avogadro numbers. Number of electrons is typically Avogadro number per mole, and then these electrons are basically classical. You can use kinetic theory, Boltzmann statistics, and all that thermodynamic principles to explain their behavior. So, that is the fundamental tenet of free electron gas model. Later on, of course, when quantum mechanics came in, people modified these classical assumptions and introduced quantum mechanics, and we will come to that as we go along. Now, the one thing that in addition to this free electron assumption of a gas of electron, classical gas, one has to also assume and find out how the electron moves about in the solid. And since there are these ions, heavy ions sitting static at their positions in this approximation, the electrons will collide with them. The ions carry a positive charge, the electron carries a negative charge. So, the collision is fairly strong, and although the Coulomb interaction between electron and the ions are not included in this approximation, so are the electron-electron interactions. Remember, the electrons are negatively charged, they also interact with each other via Coulomb interaction. So, both these interactions, electron ion interaction and electron-electron interaction, are neglected. Only thing that happens is collision of electrons with the ions, heavy ions. Now, the other assumption is that between two collisions, the electron basically moves freely. Now, if there is a electric field applied to the system, then of course, the electron will move under the influence of this field. So, between two collisions, it is under the influence of the field if there is a field applied, both electric or magnetic, and sometimes both. Now, the collisions are assumed to be instantaneous. This is the only way the electron will achieve equilibrium in the solid, because there is no other interaction allowed. So, the only interaction that it has is this collision, and through these collisions the electrons will reach their equilibrium. So, another very important approximation is that immediately after each collision the electron emerges with a velocity that has no relation to its velocity before the collision. So, an electron comes with a certain velocity, collides with an ion, and then it loses memory of its previous velocity completely. So, it emerges as if it has just it is a its velocity is completely new, in the sense that it has no memory of its previous velocity, and it's completely the direction of its emergence is completely random. So, the velocity gets randomized after each collision. So, this is a very strong assumption that it has no memory of its state, its configuration before the collision as it emerges from one collision and every collision. So, this with this assumption one proceeds further and then assumes of course that between two collisions there is a certain time that is that the electron remains free, and on an average this time is called the relaxation time tau. So, between so the electron collides with the probability of tau in collides the probability 1 by tau in unit time. So, the probability that it collides in a time delta t is delta t by tau. So, under these assumptions one can now calculate the transport property of an electron as Drude did. So, let me just show you how this calculation goes. So, what we want to calculate is the DC conductivity. Under this free electron approximation along with the relaxation time approximation. So, how does one do it? Well, it is fairly simple. Now, we know that if there is a if there is an electric field E, then it is connected to the current density by the resistivity, right. J is the current density, E is the electric field, which also implies that J equal to sigma times E, where sigma is the conductivity, which is inverse of rho. E is electric field, and J is current density. Which is basically the amount of charge that flows across a unit area normal to the flow direction in unit time. So, let me just show you what it is. So, suppose I choose a cylinder whose area here is 1 A, this area is A, current is flowing in this direction. In that case the amount of current that flows in unit time across this area will be given by J. So, that is the definition of J. So, let us just calculate J in this geometry. So, how many electrons will pass through this area in unit time? Well, it is simply those electrons that are within a distance of the velocity v, because that is the distance one covers in 1 second. So, that those many electrons will cross this area A in unit time. So, that means the current density J is V times the area A times the density of electrons. So, these many electrons are going to cross, but I need the charge density. So, I have to multiply by this per unit area. Okay. So, this is my current density for this system, where you have a current that is flowing along this tube, for example, along this cylinder, and this is then the current density. So, A and A will cancel, will give me N E V. So, let me repeat, it is the number of electrons that cross this area per unit time divided by the area. So, number of electrons which will cross in unit time are those which are within a distance of V from this end. So, this distance is V, all of these electrons will cross it in unit time. So, that is exactly what I have done here. I have multiplied this volume V times A, the magnitude of V times the area is the volume times the density of electrons, that gives me the number of electrons in this area, in this volume between this surface and a surface here at the distance V. So, this gives me this number divided by the area times the charge of an electron, which is minus E. So, that is what it is. Now, what is V? Now, V of course, in relaxation time average is something that you acquire between two collisions. So, once a collision takes place, you are basically losing your memory of your velocity. Then what happens is that there is an electric field. So, after you emerge from the electron emerges from one collision, this electric field drives it along the direction of the field. So, that is what I have to calculate, and in relaxation time approximation I can easily calculate it, because that is the charge times the field by mass times tau. So, that is the velocity. So, once that is the velocity that you acquire on an average. So, I put an average here, and that is what I will put here. So, J equal to then minus N E square tau by M into E. Now, from this relation I can read off easily that sigma is equal to N square, this becomes plus because there are two negative signs, N square tau by M. So, that is the formula that one uses quite a lot even today, more than 100 years after it was written down, and it works for many metals quite well. Of course, it has its pitfalls, it will not work in a large number of materials also, metals particularly, but it is certainly a good formula to start working with. Now, tau is typically of the order of 10 minus 14 to 10 minus 15 second in a typical metal, typically. Now, one can go further and one can actually find out the equation of motion of an electron in this relaxation time approximation. So, let us just try to do that. Now, what we do, we have this solid and zillions of electrons are scattering off this solid. So, they are coming, they are scattering off, and as I said, they lose their memory the moment they scatter, memory of their previous velocity as they scatter after the emerge from one scattering. Okay. So, under this assumption, what I need to know is, suppose an electron scatters at time t. Then in the next interval of delta t, which is very small comparable to tau, what is the momentum of this electron? So, suppose an electron has a collision at time t, its momentum at time t was just emerging from the collision at time t, momentum was p of t. It has to be a function of time. Then there is a force due to electric field, which is f of t times delta t will be the normal momentum of the momentum of the electron if you follow just Newton's law, classical physics. Now, of course, this is fine, but the fact is that not all electrons will survive, because in next collision this momentum history will be obliterated. So, we have to find out how many electrons, the survival probability in time delta t, that it has not suffered another collision in time delta t. Now, what is the probability of suffering a collision, suffering a collision in delta t? This is simply delta t by tau. Then it is survival probability that it has not suffered a collision is 1 minus delta t by tau, and these are the electrons, that electron which has not suffered a collision will pick up this momentum in the time interval of dt. So, that will be my momentum at t plus dt. Remember, dt is very small. There are corrections to it, which let us not bother about it. The corrections can be shown to be of the order of dt square, but from this equation let us just expand and keep terms only up to dt, linear in dt, because dt is small. So, this is p of t plus f t dt minus delta t by tau p of t, and this term is delta t square order. So, these are of the order of delta t square. So, those I neglect. So, then what I do is that I just rearrange terms. Is equal to f t minus p t by tau. Now, I take a limit delta t dt small So, going to 0 means in the with respect to delta tau it is small time. So, so in that limit I can write this as dp dt minus p plus p t by tau equal to f of t. Now, f of t is minus e times this. So, that gives me the equation of motion in the for the electron under relaxation time approximation. Now, you can easily check that if there is a steady state, then I can neglect this, because there is no more time dependence of the momentum, and then of course, we will in the steady state we can figure out that we will again get back this equation, that sigma equal to n square tau by m, because you can just check for yourself. So, this equation is actually a central equation in the Drude model, that you can write down an equation for the momentum of the electron under this approximation. So, this is called the relaxation time approximation, and this is how it works. Next class we will work out certain properties of this equation and find out the the Hall effect for example, and the conductivity at finite frequency and so on. Thank you.